Let's discuss question number 5 from test 8. This is from machine design. In a thick film hydrodynamic journal bearing the coefficient of friction, what happens coefficient of friction? How does it vary with the load? Okay, so hydrodynamic bearing, well, you have a shaft, okay, which carries radial loads. Okay, so I'm just drawn the shaft like this. Okay, and you have a oil between, so this is your bearing and this is your shaft, and you have an oil between. Well, as the shaft moves, rotates about its axis, it drags the oil, and there's a formation of wedge, and where the entire pressure builds up, and so the pressure that builds up supports the radial load. Well, that's a simple hydrodynamic theory. Well, now this theory is dictated by empirical, obviously, because the physics is quite complicated. You can't just simply apply force balance and just do it, because there's a fluid also involved. So people have done a lot of experiments, and the best way when the physics is complicated is to apply non-dimensional analysis. People have done that, and so what they observe is that the coefficient of friction, one of the non-dimensional parameter that is there in this physics, is Zn by P, where Z is viscosity, N is speed in RPM, and P is the bearing characteristic pressure, which is nothing but load by the length into the dia. So the load factor comes in the pressure, and this varies. The coefficient of friction with respect to Zn by P varies something like this. Well, this is a standard thing which has obtained from empirical analysis, and also it is backed by non-dimensional. So this is what we need to accept. Well, what happens is that somewhere here, these two lines, well, below this you have thin lubricated region. Thin means you may have some chance of boundary contact, metal to metal contact. Then there's a transition range here, and after that there's a thick lubricated, or you can say this is boundary lubricated, this is transition, and this is lubricated, I mean hydrodynamic lubricated, and then you have thin and thick based on your thickness. Okay, so we are going to look in this part. This part is the thick lubricated. Now as I increase the load, the P will increase, and Zn by P, so say suppose you are here, as you increase the load, P is going to increase, Zn by P as such will decrease. You're moving in this way, the coefficient of friction is coming down, so the coefficient of friction decreases with increase in load. So that's clear from this graph. So once you know this graph and you know the reasons in it, everything is clear. So the answer is B. Coefficient of friction decreases with increase in load because Zn by P decreases, and mu almost very parabolically, I would say linear or parabolic, but the curve shape is like this. Thank you.